Dear students, we are meeting after a long time. Hope all of you and your family members are safe and healthy. Now, the objective of this lecture video is to cover the remaining portion. Well, let me refresh you my last couple of classes. The first law of thermodynamics for open system, where we have covered the first law of thermodynamics for a control volume, and the derivation was in this particular form. Hope you remember that for a control volume, the equation is heat flow rate minus work flow rate plus summation of mass flow rates at the inlet into bracket minus summation of all mass flow rates into the bracket. Hope you are aware of the bracket terms, where HI stands for enthalpy at the inlet, kinetic energy at the inlet, potential energy at the inlet. Similarly, we have enthalpy at the exit, kinetic energy at the exit, and potential energy at the exit. Later on, we have defined a steady state process with certain set of assumptions that mass flow rate in a control volume is 0. Since this is 0, its corresponding energy is also 0. And from continuity equation, we have written that summation of mass flow rate at the inlet is equal to summation of all mass flow rate at the exit. And based on that, the first law equation reduces to this form: Q dot Cv plus summation of all mass flow rates at the inlet into the bracket terms is equal to summation of all mass flow rates at the exit, the bracket terms, plus work flow rate at the control volume. Now, for a single mass flow in and mass flow out, we have mi dot is equal to m dot e is equal to m dot, and the equation finally reduces to in this particular form. Okay, and we have given the examples of steady state processes as heat exchanger, nozzle or diffuser, throttle, turbine or compressor and pump, and power plant and refrigerator. In that, I think we have already covered a numerical on heat exchanger, which I will not be taking right now. I will be directly going to the second steady state device, that is nozzle. Okay, here it is. Now let me start with the statement and then I'll elaborate on the analysis of the first law equation. Now the question is, steam at 0.6 megapascal and 200 degrees Celsius enters an insulated nozzle with a velocity of 50 meters per second. It leaves at a pressure of 0.15 megapascal and a velocity of 600 meters per second. Determine the final temperature if the steam is superheated in the final state and the quality if it is saturated. Now note down the statement. Meantime, I can elaborate on what is given data. The given data is 0.6 megapascal and 200 degrees Celsius at the inlet along with a velocity 50 meters per second. And at the exit, we have 0.15 megapascal as a pressure and velocity as 600 meters per second. Now what he wants is to determine the final temperature if the steam is superheated. So here we have to first make sure that what is the phase of the steam at the exit. If it is superheated, then find its temperature. Otherwise, if it is saturated, like saturated liquid, saturated vapor or saturated liquid vapor mixture, then we have to find the quality. So since he has asked quality, obviously the phase is in mixed state. Okay. With this, let us move on to solving. Now the given data, again I have written it like this, where heat transfer in the control volume is 0 because he has mentioned that nozzle is insulated. Work transfer is nil because there are no moving parts in the nozzle. Potential energy at the exit and inlet both are same because from the common reference both inlet and exit are equal. So this is the sketch of the nozzle. As you can see that nozzle is like this, represented by this particular diagram. Now where the inlet conditions are given, velocity, pressure and temperature at the inlet, and velocity and pressure at the exit are mentioned. Now the analysis is that when we substitute all these into the first law equation, the first law equation reduces to this particular form. Only it is enthalpy at the inlet plus velocity of the steam at the inlet is equal to enthalpy at the exit plus velocity of the steam at the exit. Rest all terms vanish. So now solving for enthalpy of the steam at the exit and referring to property tables, we have enthalpy of the steam at the inlet is 2850 because we know the pressure, we know the temperature. Based on that we can define what is the phase, and depending on that we can find what is HI. So obviously, since comparing pressure and temperature, the steam is supposed to be superheated. From superheated table we can find the value of HI as 2850 plus in the bracket we have only the difference of the kinetic energy or velocity terms, which is 50 as the initial minus 600 as the final. So the terms are written over here, and you know why the 1000 is taken over here is to convert meter square per second square into kilojoule. The conversion is also shown over here. So substituting this and calculating, we can find the exit enthalpy as 2671.4 kilojoule per kg. Now the task is to decide what is the phase of the steam after it comes out of the nozzle. So for that we can use, since HE is less than Hg, that at 0.15 megapascal, that is the exit pressure, we have a mixed phase. Hence quality is to be calculated. So since it is not superheated, no need to calculate temperature. Since it is in the mixed phase, we need to calculate the quality, and hence the enthalpy is calculated based on the quality by this equation, where we know the value of H, what you have calculated right now, HF at 0.15 megapascal plus X is to be calculated, HFG again at 0.15 megapascal. So substituting this, we get the value of XE as 0.99. This is the final solution.